the labs, right?
Exactly, yeah. They take way more time than they should do. It leaves us with so little time to the important courses. Not that this is not important, but the fact that it's 1 or 2 credits, but this will have 3 or 4, too much time.
Yes, I totally understand. So it's like a personal problem you have, because in your case, you had so many labs taken the spring. It's not like the spring semester was longer for a reason.
Yeah, for pre-meds in general.
Yeah, okay, because usually you take the same courses. That's why you're generalizing.
True.
So now I do understand your nickname now, the angry face.
We already explained it though, doctor. It's not about anger. بس يلا ماشي.
Yes, I do remember. مظبوط قلت لي. All right, anyway, so I want to start lab 9. However, probably you guys have some questions for lab 8 because we never met. Okay, Priscilla. Yes. Yeah, I don't have your numbers saved. So for me, they are 2 different people. But I know I can see your name very easily on the lab reports. Like when I grade you, for example, this morning I was grading Andrew. Andrew, please read the comments. I cannot remember. All right. Anyway, so what I was saying is the following. I want us to start lab 9. However, if you have any question related to lab 8, please let me know. I know probably you did not start, and I know that some of you already asked many questions related to lab 8 on the group. Please let me know if you have any concern. I'm actually grading lab 4. Lab 4 is collision. I'm grading collision. What is it? Not lab 4? But it is lab 4, I think. Yes, I'm grading collision.
Collision's lab 4.
Yes, I'm grading the impulse momentum theorem. That's it.
Dr. Momentum.
Yeah. This is what I'm doing. Actually, I finished it for all the classes last week. It's only your class because you had off last week. So that's why we're a bit late. So I assume no questions for lab 8? Can I assume?
I actually do, doctor. عندي كم سؤال عم بحضره هلا وفي كم شغله ما فهمتها.
طب let's do that now before we start. So let me open the manual because it's faster for you to start working as soon as we finish. Lab 8 is my favorite, by the way. I love it. So easy, so clear. Where is it? Buoyancy. So what's up with lab 8? What problems do you have? Go ahead.
Okay, so doctor, أول شغلة ما كتير فهمت شو ال N, what's its relationship with lambda and L, and how do we do that to based on a fixed to end or open end? How does that change?
Okay, just a second. I had a mind buoyancy. Okay, so I think in your case, I'd rather, okay, I'm gonna open the lab report. You're talking about standing waves. Okay. Are we talking about this one, or you need to know in general what's happening?
لا أنا بعد ما بلشت الريبورت, so I don't know what it is. بس in general شو ال N, how does it relate to L?
Yeah, this topic is a bit tricky, so let's take some time to discuss it. Can you see it? Simple harmonic motion, right? No, not simple harmonic motion. Why no? Waves, linear data analysis. شو اسمه? Standing waves. It could be still on the desktop. We did it long time ago. How come I did not close it yet? Okay, let me check again. Probably I have a different folder open. Standing waves. Okay. I'm gonna open any section. No, not this one. I need to open the PowerPoint. How come? Okay, I'm gonna open section 3. All right. First of all, you need to understand that I started explaining in general that standing waves on a wire. All right. For a standing wave on a wire, both ends are fixed. When both ends are fixed, you have full loops like loop 2 and 3. Each loop has a length of lambda over 2. So in this case, you have 3 lambda over 2. In this case, you have 4 lambda over 2. That's in the case when you have 2 closed loops, 2 fixed ends. In the case where I have a tube, in our case, this is what we have. We have one closed end with a piston, and the other end is open because you have a speaker in here. Okay, so you will end up with half a loop, 1 loop and a half, 2 loops and a half, then 3 loops and a half, and so on. Okay, So if you want to count how many lambda over 2, you'd rather count how many lambda over 4 you have. One full loop is lambda over 2. Half a loop is lambda over 4. So you will end up with 1 lambda over 4, 3 lambda over 4, and 5 lambda over 4. This is in the case when you have a tube with one open end. I did not do 2 open end. However, they exist when you have a flute and the end is open. This is 2 open ends, you know? And we're not gonna cover when you have 2 fixed ends because it only works when you have a wire. When I have a tube, and especially when you have a speaker or something creating the sound at the beginning, it is actually an open end. Fine? So in your case, who was asking? Andrew, I suppose?
Yes.
Okay. In your case, don't take into account that L is n lambda over 2. You'd rather take into account that L is n lambda over 4 and n is an odd value. In the other case, it was an integer, so it could be 1, 2, 3, 4, 5. In this case, it's only odd, so 1, 3, 5, 7. By the way, we're not supposed to write it as such. In the course, you're gonna write it as odd lambda over 4, and odd should be written as 2n minus 1. 2n is the even, minus 1 is gonna be odd. You can do plus 1, but I want to start from 0 or from any value. So 2n plus 1 or 2n minus 1 is actually an odd value times lambda over 4, but we're not gonna take that just to make it easier on us. We're gonna write it mathematically, L to be n lambda over 4, where n is an odd integer. Okay, so now if you go to the lab itself, I want to discuss this. This is very important for me. You will be given, by the way, your job is to vary the piston inside the tube. Like for example, you have one certain frequency and you can see it in here, one given frequency, and you can hear the sound, you know? Your job is to find for which length of the tube you have resonance. So you're not gonna change lambda, you're gonna change the length. You will try from the biggest length and go down. Every time you have resonance, the sound is gonna be high. Every time you have no resonance, the sound is gonna be low because of chaos, you know? In other words, let me go back to the wires, and the wires are here, I think. Yes, you see those 3 loops? Those 3 loops, they will give you a very high sound. And those 4 loops will give you very high sound. If I give you a wavelength in between, it's gonna give you chaos, and this chaos is gonna somehow cancel out the sound. It's gonna be very low. So back to the table, this table, I will put the piston, I will move the piston, we'll start from 1 meter, which is 100 centimeters, and lower the length, make it shorter, 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 shorter. When I hear a very high sound, it means I have resonance, and resonance for me, I have a standing wave. By the way, I don't need to use my ear, which is a human sensor, and it could induce some human error. I can use the function and the oscilloscope. I have a microphone, the oscilloscope, it's gonna give me a high signal. High signal means I have a standing wave. A standing wave means L is N, which is odd lambda over 4. Why over 4? Because I have an open end. Okay, and then, but I don't know how many ends I have. I'm gonna say N lambda over 4. And then I'm gonna keep on decreasing to find the next length, the directly next length that would give me resonance, and then the directly next length that would give me resonance. I don't know how many lambda over 4, I don't know how many lambda over 4, I don't know how many lambda over 4, but I know these are consecutive, which means the difference is lambda over 2. Let me show you the tube again. Where is it? Here. The difference between this case and this case is lambda over 2. The difference between this case, 2 consecutive lengths, is lambda over 2. You see? So please stop me if you believe this is Chinese, because probably if I use a different language, it's gonna be easier for you. Okay? Then I change the frequency and I find the different length. Higher frequency means smaller wavelength. It means that the loops are smaller. That's why I can fit in the more lengths, you know? Probably this is half a loop. This is 1.5 loop. This is 2.5 loops. So through, like I have so many cases because of the very small lambdas, and here as well. Okay? You're gonna watch the recorded session again So Andrew and everyone else, and let me know if you still have difficulties. So far, you're not supposed to be following the wire. The wire is only to explain in general what standing waves are. Our case is this case, the case of the tube that is where here. This is our case, the tube. Okay, that is closed from one end.
Okay, فهمت عليكي. بس سؤال.
Yes.
So in the table قد ايه الان قدر نلاقي اللامدا؟ The table تحت we have the L we want to find the lambda معاك؟
ما بنعرف بس بنعرف شغلة واحدة, and let me use a pen to draw it. I know that the difference between these two is lambda over 2. يمكن ما فهمت علي.
وهي كل lambda over 2 is 1n معاك؟
أنت you don't need n. Why do you need n? You need lambda.
Based on the formula.
Okay, so أنت if you go to this side, your job is to find lambda over 2 and then lambda. خلصت.
Okay, great. So بين 69.3 what's the other value that اللي lambda over 2? أنا عرفت إنه الفرق بين الأولى والثانية هي lambda over 2.
That's why
what's
you
the
have,
first value?
Yeah, that's why you have 2 empty slots in here. This is closed. You cannot find it.
Okay, great. هلا فهمت. Thanks, doctor.
All right, so you take 2 consecutive. The difference, هلا you can calculate n. Most probably, this says n equals 1, n equals 3, n equals 5, but I don't have means to measure it. And I'm not sure because I cannot see it, but you can calculate it. Knowing lambda, knowing the length, you can deduce n. When n is an integer, يعني with some sources of errors, you will end up with a decimal, and that's confusing. That's why we found that so much easier to do length 2 minus length 1, then length 3 minus length 2, and to assume it's lambda over 2. This is the most precise strategy. You see what I mean and why we did that?
Yes, أكيد أظبطنا هيك.
So if I need to continue, آخر part, they want you to fix the frequency and to fix the length and to count how many minima. And هيدي يمكن تلاقيها صعبة. You have to move the microphone. بصير الميكروفون you pick a certain length, right? 72. من وين جبتها هيدا اللينث؟ جبتها من هون، من هيدا التيبل. Like I tried ليه 72؟ هيدا التيبل. All right, I tried 72, I tried 55, 38, 20.5, and 3.0. Wholly already I measured them. So now I fixed the length. My job is to measure n. N is what? Is the number of the extremum, يعني minima and maxima. Like here I have 1 maxima. Here I have 1, 2, 3, minima and maxima. 1, 2, 3, 4, 5. You see? 1, 2, 3, 4, 5, 6, 7. So this is what I'm counting. Maxima is the one that will give me very high on the oscilloscope. Minima the one that will give me very low on the oscilloscope. بعد كم وحدة. So بيكونوا nodes or antinodes. However, I'm saying something wrong in here. The microphone gives me exactly the opposite. When I have a node, a displacement node, يعني the oscilloscope will give me a maxima, not a minima, because it measures pressure. And there's a slide and a section in the recorded session. I'm explaining the difference between displacement and between pressure. Okay, لأنه the microphone does not measure displacement. It measures pressure. If you believe it's a bit confusing, it's only the opposites, okay? And probably it was explained in here. Let me show you the best, this one. I'm explaining what's an antinode. Antinode is the big loop, like the center of the loop. The node is the 0. It's a displacement node. And then I said the displacement antinode is a pressure node. And the best way to explain it is probably here to show you how the thing is moving. Okay, I was explaining to your friends that the motion is, sound is longitudinal. So high, like the antinode will give you high displacement, maximum displacement. And since the displacement is parallel, this is a wire, it's a transverse wave. The sound is a longitudinal wave. So the displacement is forward, backward, and not up and down. And in this case, I also have a displacement in this direction, displacement in this direction, I will have very high pressure in here. So the microphone will give me very high something in here. That is a displacement node. So nodes and antinodes are opposite for displacement and pressure. Okay, I know for a fact that I'm explaining it fast, but throughout the recorded session, I was going slow through it. So while you watch it, probably you're gonna understand it very well. And don't worry, we can extend it, especially for your section, and I can explain it again if you need me to, okay? Yes, N in the last table, N is the number of maxima and minima together. So I'm gonna move the microphone throughout the whole length, that is 72, and count how many maxima and minima. And they are actually alternating. So maxima, minima, maxima, minima, maxima, minima until the end of the tube. So N is the total number of maxima and minima. Call them anything, you know?
Sorry, اتفضلي.
Yeah, I'm done. Tell me.
The intersection between two waves is considered a maxima أو minima. لما اشوف لك عم تعديهم عم تحطي نقطة على الانترسكشن between two waves ونقطة ثانية وتكون في max one wave على المين.
All right. If I need to take this diagram into account, this looks transverse, okay? The microphone will measure here a minima, and it will measure here a maxima of pressure and a minima, all right? So minima, maximum, minima, I will say n equals 3. Here I have minima, maxima, minima, maxima, minima of pressure. So it's 5. So yes, that's true, Andrew. We have a maximum in displacement, which is a minimum in pressure. يعني ما في شيء غلط، اثنيناتهم صح. The maxima in displacement is the minimum in pressure, and the microphone measures the pressure. يعني the opposite. But who cares? As long as I know how many, and as long as I know how to locate them, it's okay. All right? Sound waves are so different.
Thank you, doctor.
Yeah, sound waves, my dear friends, are so interesting because all different waves are transverse. Can you think of any other wave that is longitudinal? It's only sound, or probably if you can create one in a slinky. But around you in nature, you don't have a longitudinal wave. So sound waves are so interesting because of that. And on top of it, we cannot see them, you know? I know light wave as well, we cannot see them. Even if we can see the light, we're not supposed to see the oscillation of electric and magnetic waves. But sound wave is really interesting. That's why the only way to measure it is through a microphone or through a pressure sensor, you know? Yes, anyway, I know that this is not final. We can revisit again, especially for your class. I'm more than willing to meet with you individually if needed, or just give me a message and we can meet for 10, 15, 20 minutes. You want us to draw a longitudinal wave and label nodes and antinodes? Yes, if you want, you can draw a transverse wave because it's symbolic, and you can tell me where the pressure nodes are and antinodes, and where the displacement nodes and antinodes are. Okay, if you want, how would you draw a longitudinal wave? If you want to draw it, probably you want to put points to show high pressure, low pressure, high pressure, low pressure, or arrows. It's up to you actually. If you want to do them loops, it's okay, just label them. Okay, I know this question sounds not clear because we wanted to give you some freedom around this this idea. You can draw anything you want as long as you show the nodes, antinodes of displacement and of pressure. Okay, anything else? Look how active you are. مش عم لاحق questions. يلا, ask me more. And today the boys are active. وين Priscilla? All right, the outline. What is linear expansion? All right, so we're gonna discuss linear expansion. Yeah, coefficient of linear expansion, because by the way, the title is coefficient of linear expansion. You will be given 3 rods. You have copper, aluminum, and brass, if I'm not mistaken. You're gonna heat them up, or I'm gonna do it on the video. You're gonna watch me doing it, and you can measure the length before, after, and so on, and find the coefficient of linear expansion. The lab is easy, the idea is easy, The lab report is easy as well, okay? We need to discuss the setup quickly, the lab report as well, and I'm gonna discuss a bit the coefficient of volume expansion because you will be asked about it. I will not give you answers, but probably a starting point to start from somewhere. Now you tell me, what is linear expansion? I know that I already told you, but how do you see it, and it's due to what? Go ahead, I'm all ears. Okay, due
temperature.
to heat. Okay, when the temperature increases or due to the addition of heat to the system, what happens? Are we talking solid, liquid, or gas, or all of them?
Maybe we can start with solids, the particles, the metal part. No, I don't know. It will expand because they gain kinetic energy and they start bombarding with the surface. I think, I'm not sure. They start bombarding with the surface.
Yeah,
so-
that's the microscopic explanation of what's happening. It's great to discuss solids first because we're dealing with linear expansion. We cannot really talk linear when we have a liquid. We talk volume for gases as well. But yeah, everything behaves in the same way, but we have some exceptions. It's due to the, due to the Boltzmann theorem, that temperature is related to the kinetic energy or to the RMS speed of the particles. And definitely you will have some linear expansion. Okay, so this is an example how we ended up. So if you read the caption, it says thermal expansion of long continuous sections of rail tracks and is the driving force for rail buckling. This phenomenon resulted in many, like those rails were actually not functioning anymore because of the expansion due to heat. All right, and this is a way this is a bridge. Thermal expansion joints like these. This is one example. Now with civil engineering, they have different ways of creating some space to take into account the linear expansion due to heat, because between different seasons you have a very big drop or a very big increase in temperature, and this should be taken into account, especially when you have bridges and rails and so on. All right, so this is without buckling, so for it to take into account the space. So this is basically linear expansion. Now we need to discuss the coefficient of linear expansion. This is a table for different materials, so it's material dependent. By the way, I would love to talk about water later on, and I have some slides about it. Water is a very interesting material. It creates a certain exception. I don't know if you know about it or not, but it will be good if we talk about it for just a bit. How do we find the coefficient of linear expansion? We follow this formula. By the way, you can replace dl over dt, which is the rate at which the length is changing with respect to temperature, if I have a linear change in length, like a constant change in length. And we can assume that. So your job is to find the drop or the increase in temperature. So you measure temperature, initial temperature, final. You measure length, initial length, final. And you measure the initial length. So we need to measure the initial length of the rod prior to starting the experiment, and sometimes we forget, so we need to wait for it to cool down. By the way, we don't really need to wait because delta L is very, very small. It cannot be seen with the naked eye, and it will not be measured with a regular ruler. It will be measured by a special micrometer or dial gauge, I would say, because with a regular ruler, probably you cannot see the tiny increase. That will be a fraction of a millimeter. And this is how you find the linear expansion. Can you guess what the coefficient? Can you guess what is the unit for the coefficient? Can you try? If you look at the equation, this is so much easier. What is the unit for the coefficient? Meter Kelvin, not true. It's easy and obvious. Check again. Exactly. By the way, you have meter over meter, it cancels out. So it is 1 divided by the temperature drop or temperature change. By the way, temperature change can be degree C or Kelvin, because you know the jump in Kelvin and the jump in degree C is the same. So if you ever see degree C to the -1 or Kelvin to the -1, both are equivalent, because we're talking about an increment, like a change, not an actual temperature. All right, you can see some values here. Aluminum apparently increases in length much more than in VAR. Let me check the powers. Glass, obviously. Yeah, so yeah, aluminum is the one. No, you have lead. Lead actually increases a lot. By the way, I wanted to keep this table with you for two reasons. Reason number one, I want you to see that the thermal expansion is temperature dependent. Wow, this was confusing for me, because anyway, the temperature is changing. So probably you can think a bit about this one. I read a while ago that it's gonna change slightly with temperature. So it's not like it's a constant. Question mark, think about it. Also, I wanted you to see that you have linear expansion, the coefficient for linear expansion and the coefficient for volume expansion, both of which have the same unit. And probably if you look at both, you can find the relationship. I don't know, question mark, think about it. Okay, I will keep that for you. Probably you can find questions like these related in the lab report. Now the setup. What do we have? First of all, we have this container, okay? It's a steam generator. It's basically a container. You put water, tap water in it, and you click on, and you can put the power to any, you have 0 to 8 to 9 to make it faster or slower. This is the power of it. And you wait for water to boil. Meanwhile, you can close your container tightly, and it has two openings. If you want both openings, you need to collect steam. That's the point. Usually we use only one opening. So we use two tubes, one tube to collect the steam, and the other tube we actually close it. And we have many ways to close the tube, you know? So this is the steam generator I will be using. By the way, those pictures were found from the catalog. I'm gonna show you the real equipment we have that are actually the same, basically. You have 3 rods to play around with. I know for a fact that the white one is aluminum, the red one is copper, and the remaining one is brass. You can put them as such, but this is only a stand, because if you want to do the experiment again and again for the different type of rods, you need to move the rod to be the first for it to be attached to the dial gauge. Look at the dial gauge. The dial gauge is very sensitive. I was so happy to see that they got us digital dial gauge. Last semester, we were dealing with an analog one. There's no difference actually. The digital one was giving me a hard time because it was switching off every second. I did not know why. It was very easy to zero though. You just have to click on the 0 button, and I'm gonna show you how, because every time you touch it, it's gonna give you a different measurement. So whenever you build your setup and you have it ready, you click on 0. Digital sounds easy because you can see all the significant figures. For the analog measuring tool, it was difficult to zero. So we used to measure, measure the value and minus the initial measurements, and it was very precise and accurate and fine. And we used to find the smallest subdivision divided by 2 to know how many decimals we are allowed. And the unit was displayed on the thing, you know, where you read from the needle. This one you have a unit as well. I can show you in a moment. So the dial gauge cannot be on any rod. It's only on the first rod. That's why when you finish playing with the first rod, you need to put it away, or maybe wait a bit for it to cool down, and then put it away and put the white one instead. Fix your dial gauge, zero it, and try again. This is the tube. You're supposed to connect the tube from one opening of the steam generator into the rod. The steam will go through the rod, and you have some water vapor or steam escaping from the other end. In the old setup, the water vapor used to condensate and we had drops of water falling on the desk. So we have a tiny container to collect it. Otherwise, it's gonna go on your tablets, your calculators, your papers. But for this experiment, the new equipment I tried like 2 Mondays ago, it was only steam escaping up. So it was interesting to see. I'm gonna tell you how we need to measure the temperature later on, okay? So this is a picture of the setup. This is a different picture where you can see the gauge. You can click inch or millimeter, on, off, and 0. You see how easy to manage? I think this is 1.10 millimeters. And that's how much it has increased. This is a screenshot from the video. I think, I can't remember the values, but you can see it, but I think that was 1 point something millimeter, yes. All right. What else? So you see the tube going into the rod, and you see the dial gauge on the other side. The dial gauge is resting on a ring, so when the ring would move away, the dial gauge will give you some values. Yes. Now you can see a multimeter. This will be used as an ohm meter. And what you have in here under this foam material, you have a thermistor. And a thermistor is a resistance that varies with temperature. And you can measure the resistance easily. And then you will be given a table that will give you for each resistance what's the temperature of the rod. And this is so cool. At the beginning, when we started the experiment, it was between 22 or 23 or between 21 or 22. I can't remember. You can see the video because it was giving me a value between those two values in ohms, 11 something thousand ohms to 11 something thousand ohms. So by reading the measurements on the ohm meter, you can tell the temperature following the chart. This chart was found online. Probably I can show you. This is a screenshot of what I had in the experiment. So it starts from negative 10 degrees C up to, I don't know, 50, 45. And then when you turn it backwards, you can see all the temperature up to 100 degrees. Since I'm dealing with steam, water vapor, I'm gonna reach a value very close to 100, probably 95, 98 degrees C. So I need to turn the table to see what's behind. So T initial will be around room temperature and T final will be very close to 100. Okay? This is the lab report. Your job is to measure the length of the rod before the experiment. Then you need to measure the resistance at room temperature. And then find, okay, let me pick a pen. So when you find the resistance at room temperature, you can find the temperature from the table. Why did I write 0 degrees C? Probably I meant degree C, all right? And then you can find delta L from the dial gauge. Be careful to add uncertainties. Follow the video to check if we're dealing with a digital measuring tool or an analog measuring tool. Now your job is to find R hot. You're supposed to wait until you will reach a constant temperature or a constant elongation on the dial gauge. This is where the rods cannot go longer anymore. And you find T hot from the table. Delta T is basically T final minus T initial, very easy. So this is T initial, this is T final, okay? Now back to the equation to find alpha. You have delta L over L times delta T divided by delta T, okay? So some questions would be, okay, the questions are not here, but let me show you in the manual. Did I close the manual? Not. Okay, so in the manual, you have very simple questions. Calculate alpha for copper, brass, aluminum, and I don't see many trials. You will be surprised when you will see that the lab report is very short. The reason is because it takes forever to boil the water. So for you to find those values, usually you need to wait like 30 minutes. So we found it unfair to ask the students to do 3 trials of each. We expect the students to stay in the lab for a minimum of 90 minutes, and probably you need more if you need to do many trials of each. You know what I mean? To find the average and the RMS. That's why, yeah. And then they want you to calculate in this case and then probably find the measured value and compare. And you have some theoretical questions or conceptual questions, like those are conceptual questions to answer. One related to volume, one a general about a steel bridge, and one general about a liquid, mercury in a thermometer. Those are interesting questions. Probably you can do some reading before you answer them. The one-time online labs helped us. Yes, because it was easier. Actually, I was not very serious, because you will see in the video, I will tell you, don't worry if it takes you a lot of time to boil the water, because you can use the same exact water on the brass. Like you wait for the first one, but I wanted you to feel عم ربحكم جميلة يعني I did the waiting. But if you really think about it, you only need to wait for the first rod, because the water is gonna be hot already. For the second rod, you just need 1 minute for steam to be collected, and for the third rod as well. So لا ما بدها كتير وقت. But anyway, to ask for students to do 3 trials for each was time consuming, because you need to wait for the rod to cool down as well, you know. You cannot do the experiment on a hot rod. I don't know. In the old days, the equipment were not easy to handle. This one is perfect. Like you have the ohm meter ready to give you measurements, the dial gauge. In the old times, we had to put an analog dial gauge, and we need to calibrate it every time we touched the equipment, and so on, you know. So no, it is not long, really. It's a very nice lab, actually. And waiting sometimes for things to heat up will help you understand what's happening, you know, because it helps you look at your setup and analyze and observe. Everything happening slower is better for the students. Yeah, anyway, so let me continue a bit. Now, concerning the coefficient of volume expansion, I just want to give you a hint, which is why volume expansion happens, because linear expansion would happen on the 3 different directions. And I love this diagram that would show an extension for each length. So if each length is actually getting longer, obviously the volume is getting longer. So how do I find the coefficient of volume expansion? You will think about it, and you can easily find it anywhere in any book. And this diagram will help you decide what to do, okay? I need to talk a bit about water, just because I believe water is interesting for me. I don't know about you. And as you can see, it's not in the outline, but it's cool to talk about it. Does water expand or contract when heated? Do you have an idea? Do you have an answer to this question?
I think expand.
Now, how come when you put water in the fridge, in the freezer, and you cool it down, it expands as well?
How does it expand? If it cools down توصل لمرحلة بتصير كيوب ما بتعود expansion.
طب ليه بس يصير تلج بيفقع الكونتينر او it overflows؟
هيك ما بعرف.
شو يعني بطلت تعرف؟ You're speechless. Water is
Exactly.
so interesting. شو هالخبرية؟ Yes, it's mind-blowing, of course. هلا, the explanation of why it's happening is very simple, but it's very nice and cool to know this about water. The first time I realized this, I was really like not young. I was like, I've never realized this. I was around 20 something. All right, so they're discussing that water actually at 4 degrees C, it has the lowest volume. يعني below 4, it's gonna expand. Above 4, it's gonna expand as well. And this is interesting. This is the chart that gives you the density of fresh water. So at 4, it has the highest density because it has the lowest volume. Okay. And the best explanation, oh, I did not show you. I have a screenshot though. Let me find it. Forgot to include it. It's a very easy screenshot. Let me see. This one probably. Yes, that's the explanation. It's only because of the hydrogen bond. All right. So why not include it in our slides, especially that you guys are gonna take the PowerPoint away, so I can include this for you. Okay, just the picture. I forgot to include it. So basically, Yes, this one. All right. So the only explanation is the hydrogen bonding, because solid, it happens only for water, and I do understand by hydrogen bonding what you have between between the molecules of H2O, which means whenever it's solid, the particles have to be spaced out a bit. Whenever it's liquid, it can fill in the empty spaces. But eventually, when you start heating it up above 4, it's going to expand again because of regular volume expansion. Okay, but I believe it's interesting to know just quickly, and it has some applications, and this is a very interesting application. It's because of the density. You know, all substances, when they turn into solid, they become denser because smaller volume. So usually they don't float, they actually sink. And what's interesting about water, ice in water floats, and this is the only substance that has a solid that would float on the liquid phase. And since 4 degrees C is the highest in density, this is a lake, and it shows you how the distribution of temperature is whenever you are in summer or whenever you are in winter. 4 degrees C is always the denser, so it's always at the bottom of the lake. And it actually helps a lot the cycle, the flow of the water and the ecosystem and so on. All right, I don't want to waste your time talking about water because it's not relevant for our lab, but I thought if you know a bit about it, why not? Because I believe it's very interesting. Yes, so you can read if you want, and that's it. I'm gonna save as it for you and give it to you. And I will try to, I just need to give you some values. I have a lot, and that's it. I just need to make sure if you need something more than this, but I doubt. Everything else you need is in the video. Let me show you the video. The video is here, I suppose. This is an actual video, so we can fast forward through it. It was done 3 weeks ago or 2 weeks ago. These are the 3 rods. I started with brass, and this is the steam generator. One tube, the black, was connected to the rod, and the white was actually clamped with a clip just to close the steam from, to stop the steam from going out. I'm explaining how I managed to get ready with the steam generator, water tap, and then the tube, not connected yet. I will connect the tube to the rod. Not yet. It's still on the desk. However, this is on, but I know for a fact water is still cold. By the way, you can touch the tube here. If it's still cold, it means no, you don't have steam yet. You can tell how much waiting you need to do. I'm explaining that I have 3 rods. I'm explaining that this is to be able to handle the rods, and also to hide the thermistor, the thermistor under. And I explained a bit. By the way, we have so many equipment of those, and students usually damage the wire connecting the thermistor to the plug. Yes. دغري بينقطش ما بعرف ليه. I thought the students were being violent until I did one. I destroyed one. So I realized they're not user friendly. So this is a ohm meter. I'm explaining the significant figures, the scale, how many decimals. You can see 11.88 kilo ohms. So this is 1,000. And you can see the table to show you how many degrees it is. It was room temperature. It was a very cold day. I remember the wind. I told the supervisor not to show my hair because it was all over the place. It was a very windy day. Yes, so this is the dial gauge giving random something because it's not zeroed. And then I'm showing you every time you push on it, what happens. By the way, the measurement in the dial gauge probably in the video is not to be taken into account. I'm gonna give you actual values and how I'm supposed to click this on and then put it on the ring. Whenever the ring elongates, it starts measuring. And I clicked on 0 to zero it. Okay. And then I think I'm gonna put the tube into the rod, but I'm supposed to zero the dial gauge after inserting the tube, because if I touch the tube and the rod, the reading is gonna change. So whenever I finish touching the setup, I should zero. Like here, I'm zeroing again. All right, the reading is still constant. The rod is still cold. I heat up, I touch the tube. Here we pause the video. and we continued the video later after steam started flowing. This is a container in case I have water dripping, but no water was dripping and I was surprised. I think it shows that my system is very efficient, which means that the rod was hot and no condensation was happening. Probably in the other system, the old one we had, it was still cold, and that's why condensation was happening. Anyway, keep a container for the partner's sake, because you don't want hot water on the desk. This experiment is not safe. Like, we have medication for your skin. You can have any burns easily, you know? And you can see the resistance is dropping. Dropping means the temperature is rising. By the way, temperature and resistance, they behave in an opposite way. Linear or not, I suppose it's linear. However, I cannot be sure unless I plot and make sure it's a line. So I don't know if they're inversely proportional or not, but I know they're opposite. Like, when the resistance increases, the temperature decreases. And you see, I'm very close to 90 something degrees. That's 0.7 kilo, 76. I wait until temperature stabilizes, or this measurement stabilizes, and I take the final measurement. That will be T final. Let's assume you don't wait enough. It's also okay, because you need to know the length versus temperature. So any temperature and length would be good. But if you wait enough, the delta temperature and the delta L will be significant. And it's nice to have, it's not nice to play around with very small values. It's a lot of errors, you know? And that's it for the experiment. Like, now I take measurements and then I unplug and I start with I repeat the same thing for a different rod, and that's it. Yeah. So that's the video. It's not on LAU YouTube yet. I'm gonna upload it tonight. It's a new video, and this presentation will be sent to you, and that's it. We're done. I will stop recording, but I'm gonna